First things first, let's start with functions. So, we have an equation, something like 3x squared minus 5. In this case, x is our variable, called so because we vary it, whilst 3, 2 and 5 are all constants, because we keep them constant. The basic idea being that if we input some kind of number into our equation, we'll get another number out as our equality. So here's me slowly increasing the x. Okay, that's enough. Now let's represent them with bars, so height of the bar represents the value. There we go. As you can see, these two animations are exactly the same, I just represent them differently. Now let's duplicate these bars, rotate the first one, and put the second one at its end. Then if we slowly increase it... that feels kind of pointless, doesn't it? Well, it is pointless, because what we actually need to do is we need to mark the path it took, and congratulations, we've got a graph of the function. In this case we have a plane where each point on this plane represents a different combination of x and y, but only the points on this line complete the equality. So we can see that if we move our point on the line, it works, but if we get it off, our equality doesn't hold, simple as it could be. That's how the functions work, it's fairly simple. We can do it for any kind of function, so anything from just x, through a polynomial of some sorts, up to a sine wave, next we have the derivatives to talk about. So, what is a derivative? Well, derivative is a slope. What do I mean by that? Okay, well, imagine a line like this. This line is flat, it has no slope. A line like this is steep, so it has a slope. A line like this is really steep, so it has a high slope. And a line like this has a negative slope. Cool. How would we calculate this slope? Well, if we take our diagonal line and draw a single horizontal and a single vertical, we get vertical divided by horizontal. That is our slope. Now, one thing which you might have noticed is that these two lines right here are the exact same lines as before. Which means that if we get back to our function, select 2 points on it, then we can get the slope between those 2 points by just dividing these two numbers. So dividing y by x. Or actually, if we're checking the slope between the 2 points, then we'd have two coordinates that matter. We'd have the coordinates of the first point and the second point. And in order to check the slope between them, then we need to calculate these lines. And in order to make this even more understandable, let's draw up all of the lines. As you can see, here's how I vary them. It is quite trivial to see this line right here. So there we go, that's our difference in y and difference in x. I will leave it on the screen for a second because I do realize it may be a lot of values, so just take it all in. And then, if we take a difference in y and divide it by the difference in x, we get the slope. This is how they correlate. And here, just to really make sure it kicks in, let's move everything about. Simple, or at least I hope it is simple, because now that we've got the slope, in order to turn it into a derivative, we like to change it up a bit. It will still mean the same thing, but instead of noting it down as a slope between two coordinates, let's note it down as just one coordinate, and then have it be offset by some value, h. What about the y coordinates? Right here, the y coordinate would be just the function of x. That's because x is our position and f of x would be the height of the function at that position. And right here, it would be f of x plus h. That's because our position over there is x plus h, once again input it into the function to get the height. Simple as it could be. So now we have the coordinates, what about the slope? Well, that's simple enough to start with, just inputting our coordinates into the slope difference. Okay, that is a good start, but let's simplify it, because right here we have x plus h minus x, so these two just cancel each other out and just leave an h. The top can't really be simplified anymore, but that doesn't matter because if we zoom out, we've already got everything shrimple as it could be. Why? Well, it's because right now, in order to get the derivative, all we need to do is just scale the h down to 0. That is a derivative. Now, a little bit of a pause here, because a couple of you could say, make it. How could we scale the h down to 0 if we are dividing by h? You can't divide by 0, and that is true. But in this case, we have this one weird trick to divide by 0, and that is, we first solve and only then solve. What do I mean by that? Well, let's get a tad more specific. Let's say that our function is equal to x squared. In that case, we can replace f of x to x squared, and the f of x plus h to x plus h squared. I will switch between them for a second to make sure you understand how they are both equivalent, and with that in mind, we can solve it. So, first things first, we expand the brackets into our two multiplications. Then we multiply x by x, plus x times h, plus h times x, plus h times h. This does translate to x squared plus 2xh plus h squared. Then what we do is we plop it back, and you can see that we have x squared minus x squared. So right away, let's cancel them out and we get this. Now 2xh plus h squared is divided by h, so we can cancel these out with the h as well, and there we go. This is what we end up with. So if you remember that what we've been doing here is the equation for the slope the entire time, which means that this equation we end up with is also the equation for a slope. And the curious thing you might have noticed is we started with trying to set the h to 0, but we couldn't because we were dividing by it. But now we're not dividing by it at all, which means we can just set the h to 0 and we get 2x. Which means that the slope at each point for a function 2x will always be equal to 2 times a specific x. Here is the slope, and here is the position it is calculated at. And you can see that it's rising twice as quickly as the coordinate itself. So at x equals 0.5, it's rising at 1 unit per width for 1 unit of height. At x equals 1, it's rising 2 units of height per 1 unit of width. At x equals 2, it's 4, and so on, so forth. So with that one weird trick, we've just managed to divide by 0 without dividing by 0. Normally the way you do it more formally is a bit different, and by that I mean a limit, and you know what, since this is meant to be accurate, let's just talk about it, might as well. Basically imagine another function in which h is the variable and x is the constant. Since we don't know what x is, it's a bit difficult to graph it in one dimension, since it would do much better on a plane where this is the x direction and this is the h direction. Does that make sense? Same principle as with our functions before, only now we increase the x on this side and h on this side. I hope that if you think about it for a second, it will make sense. Now, creating a function that depends only on h would effectively be equivalent to just taking a slice of this function like so. Which slice? Well, that depends on what we set the x to. Lovely. So let's pick some kind of x. The exact value doesn't matter, what does matter is what we do now. Well, we take that function and we're trying to get the value at h equal to 0. However, keep in mind, setting it to 0 does mean dividing by 0. So right here on the graph, what actually happens is we have a continuous line with a gap at 0. That's because there is nothing there, because the division by 0 is undefined. So what the limit says, what kind of value do we get if we get closer and closer to 0? If we approach 0? And the answer is, we get 2x. So if we get back to our plane, and if instead of slicing it on the h-axis, we slice it on the x-axis, then what we get is... well, it's quite difficult to explain. It's basically the slope in the direction of h, where h specifies the magnitude, but that would lead us down a bit of a rabbit hole, which I, for one, am not interested in taking because it's kind of irrelevant. So instead, let's just go directly for the money shot and let's slice it at h equals 0. What do we get? Well, if we're completely mathematically strict, then nothing. This line doesn't exist because at each point here we're dividing by 0. However, if instead of asking what is it equal to, we ask what does it approach from both sides, then we get an actual function. And this function is the function of a slope at that point. Hold on, what does that even mean? Well, what this means is basically how quickly the function is changing. So you can see that derivative of a function is low near 0, and the function we started with, so x squared, is also flat near 0. As we keep going up, the derivative gets higher and higher and higher, and our underlying function gets steeper and steeper and steeper. And that is what that number represents. It represents just how steep our function is, so once again, how quickly it's changing. The most common example of this is velocity and position. So velocity is a derivative of position because velocity tells us how quickly the position is changing in relation to time. Simple enough. But if velocity is derivative of position, what is position to velocity? Well, that would be the integral. That's because integration is just the opposite of derivation. So derivation is just a kind of disintegration. How? Well, let's think about it. Let's say you have a graph of some kind of derivative. So for example, a graph of velocity. Now this tells you just how steep the underlying function is. So for example, right here that function would be flat, because this derivative is equal to 0, which means that it would actually be a pretty good start for our process. That's because if we start the function at some point, then afterwards we can bring it up. Up by how much? Well, right here, this derivative tells us how much it's changing, so we can just bring it up by the height of this derivative. And then at the next point, the function is still going up, so we bring it up by the height of our derivative as well, and at the next point again, and so on and so forth. This is because the derivative is the change, so each point represents the change, and everything always is just a sum of its changes. So we just start with the derivative where each point represents the change of the function. And if we'd like to get the underlying function, then we just need to add all the changes. If we think of it in more discrete terms, we can imagine it this way. We have our derivative, and let's say that we'd like to compute its integral, where in that case we're starting right here, a flat line. For the sake of convenience, then at the next step we have some kind of change, represented with a rectangle like this. The reason why we're going for a rectangle is because we're doing an approximation so far, and so we need to account for the fact that we missed out on a whole bunch. So we just assume that derivative was constant on that area, once again just to approximate it. In that case, we bring up our underlying function by that area and congrats! We've gotten the first step. Then for the next step, we do the same thing. We get this area, we add it to the height, then the next step, and the next, and yeah, it just keeps rising. It keeps rising because our derivative is positive, which means that the change is positive, so it has to keep going up. And so this is what we end up with. And you can see that it is actually quite a fair bit equivalent to the area under the function. And if we approximate it better with more rectangles, and more, then we get the function. And that's the integral. This just means a sum, so adding all of these together. This is just the height of our rectangle, and this is the width. You multiply them together, you get the area. You add all of these areas together, and you get the full area under the function, up to that point, and that is the integral. So yes, the integral is basically the area under the function. If we have our velocity and we want to get a position based on that velocity, then you just calculate the area under that function up to that point to get a position, except in this case I've misled you because this was actually acceleration, and as such the integral of acceleration is velocity, which itself will give the position. And in that case, allow me to represent this using a cube. So position of the cube will be the position, velocity will be this arrow in the front, and acceleration will be the arrow in the back. So this is how it evolves over time. But there is actually a pretty interesting question to be asked. Where do we start? With our cube, this property can be visualized like so. Let's say that we have the graph of velocity of our cube. From this we can get the function of position of the cube using the derivative. And right here, if we look at the animation, what this translates to is just us knowing what this arrow is at any point. The arrow is what we know, and based on this arrow we get the position. Simple, except what if we started with the position of the cube right here? What then? Well then, nothing would really seem to change. The velocity would still act in the exact same way. The shape of the function would stay preserved, but the height can change. This is due to the fact that with our velocity, we can figure out how our position changes, but not from what it was originally changing. And in mathematical terms, we note it down by saying that the integral of a function gives us its antiderivative plus a big constant c. And if you want to see a more mathematical reason for why this is the case, then going back to our equation for derivatives, put care to the fact that if we have a plus c at the end of the function, then if we solve our equation with these c's, they cancel each other out. So adding a constant to our function, no matter what constant that is, will always result in that constant disappearing. That right there is precisely why there are an infinite amount of functions that solve this equation. It's because the shape is predetermined based on this function. But we don't know what constants have been added. Simple. Now with that in mind, let's apply the knowledge we've gained in something that I have not covered yet on this channel. And that would be with solving ordinary derivatives. Yes, that's because derivatives and integrals I have covered in the past, even in the most popular video on this channel, but the reason why I wanted to make this video is because right here I wanted to start from functions and get to how these tools on the functions are used in physics. Now this will in no way, shape or form be a comprehensive list, and I have a very limited amount of time to finish these videos, but I will try to include as much as I can. So first, we can divide solving derivatives into three categories, and in this case, since integrals are just derivatives the other way, I will lump them in. Mathematicians may have some problems with it, but abusing the tools that mathematicians have spent years developing is part of the job for physicists, so that's quite appropriate. Anyway, starting with the most proper, but also most difficult, you can use the defining function to solve equations. In this case, this will give you the most accurate and direct answer, but it will lead to certain problems where it is sometimes either difficult or downright impossible to solve this equation, so we won't spend too much time on it. Next, a fair bit easier, we have the general rules method. There are a couple, but I will display these 5. If you're interested more, I can make a follow-up video, but for now, these will suffice. First, a classic. A derivative of x to the n is equal to nx to the n minus 1. This one is probably the most often used rule of solving derivatives, to the point where most people do it subconsciously. So here, have a couple of examples, and the reason why this happens we can find by solving the equation. First though, let's start by writing out a couple of things, and by that I mean a plus b squared, a plus b cubed, and lastly a plus b to the 4th dot dot dot. Now we can notice a very subtle pattern here, which may seem just like a random collection of unrelated facts, but bear with me. First term is just a brought to the power that we started with. Second term is always a multiplied by b, multiplied by the value we started with as the power, to the power of n minus 1. And then the last fact being that all of the terms from here point on are multiplied by b to the power greater than or equal to 2. Okay, these 3 facts I will not prove, because this is meant to be a physics prep, and proving is a mathematician's job. So for now, just trust me and let's move back to our equation. Here we can just replace f of x with x to the n, and the original f of x plus h with x plus h to the n. Now as the first step, let's expand that into the sum using our 3 facts. Now the first fact will mean that the first term will instantly cancel itself out with the last subtraction. Brilliant. Then the second fact is this term, and if we divide all of these by h, we get our final equation. Great. Then we need to get rid of the additional sums, and using our third fact, we know that all of these were multiplied by h to at least second power, but since we divided all of them, they are now multiplied by h to at least first power. No matter though, however, since if h approaches 0, then all of these powers will be equal. And since all of these are multiplied by 0, the entire sum becomes 0. And so there we go, we've gotten our equation. Now, I cannot accent how unrigorous this was. If you'd like, prove it for yourself. But unfortunately, due to lack of time, we have to keep going to e to the x. Derivative of e to the x is equal to e to the x. Right here I haven't really got much to say other than, well, that's kind of the whole point of the constant e. Like e as a constant, that's its whole deal. But it is a more specific sliver of the equation derivative of a to the x, which is equal to a to the x natural log of a, which, well, once again, this natural log is here because the whole point of e is this derivative. It's just a thing to keep in mind. Anyway, next we have the sum of derivatives. What do we get if we take a derivative of a function plus a function? I think it's kind of a waste of time to dwell on this too much, so I'll just show it from the perspective of the derivatives equation. Now next we have the much more interesting product rule. If we have two functions, f of x and g of x, and we know their derivatives, then what is the derivative of f of x multiplied by g of x? Well, that is a lot more interesting. In that case, let's start by asking the question of, what is multiplication? Well, if we have two values like a and b, then we can imagine multiplication between them as just an area of a rectangle with them as their sides. With the same logic, we can get back to our functions and flip them onto the other side. Now all of these arrows make a rectangle, and the area of these rectangles is the value of our new composite function. So, what is the derivative of our new function? Well, let's zoom in on two of these rectangles like so. And with that in mind, let's ask the question of, what is the difference in their areas? Well, right here you can see two rectangles that represent our two functions at two different variables. So right here, f of x and g of x. Right here, f of x plus h and g of x plus h. Now from those variables we're getting four new shapes. This rectangle right here, this rectangle right here, this rectangle right here, and this. Then for the sake of convenience, let us define two new variables, df and dg. Now with that in mind, we can see that the big rectangle is equal to f of x multiplied by g of x. The two smaller rectangles are equal to, in order, df times gx and dg times f of x. And finally, the tiny rectangle is equal to df times dg. Now the whole idea here, as always, is that when it comes to these rectangles, we're trying to check the difference in their area on as small of a difference as possible, which means that h, df and dg will all inevitably go down to 0. df and dg will go to 0 by proxy, and it is important to mention that because otherwise none of this would work, and so going back to our equation, in a derivative we'll divide all of these by dx. This is the same exact idea as with our single function, except right now our function is of area, not length. You can see that with a single function we have these three measures, and our derivative is this minus this divided by this. And in our case, it would be just this minus this divided by this. So, back to our equation, both of these rectangles contain this rectangle, so if we subtract them out, we just get a gap. And that means that all that's left is these three rectangles right here, divided by dx. So, this is what we end up with. Now, the mathematics I'm about to perform should not be classified as mathematics, considering how absolutely horrendous they will be, but for the purposes of the visualization, it really can't get any better than this, so just bear with me. Let us examine the areas we've ended up with. We lost the f of x by g of x due to cancelling itself out. We do, however, still have the three areas, dg times f of x, df times g of x, and dg times df. And in order to get the derivative, we just divide them all by dx. Like so. And then right here, this is a bit tricky, but it's kind of like multiplying a 0 by a 0 and then dividing by 0. So these two kind of cancel each other out and we get a kind of remaining 0. Now, there are a lot of asterisks, but the point stands. Two infinitesimals beat division by 1. And what we get is a 0. And so our remaining equation is this: derivative of f of x multiplied by g of x plus derivative of g of x multiplied by f of x. Simple as it could be. That is the product rule. Now, one last remaining thing is the chain rule. So what happens when we put a function inside of another function? But we'll leave that one for in a second, because first we should talk about the third category of solving derivatives, and that is guesswork. Yeah, okay, I know it may seem silly, but let's say that you see an equation like this. A derivative of f of x is equal to a constant times f of x. What is f of x equal to? Well, we can't in theory know for sure, but we can make an educated guess. And as such, what kind of function would be equal to the derivative of itself times a constant? Well, that would be the exponential, of course. Another example could be second order derivative equal to minus the function. This one you might not know, but the answer is a wave. A second order derivative of a wave is just that wave inverted, or to be more precise, sine or cosine with different waves. It doesn't get complicated, but that's the basic idea. And maybe one day I'll make a more comprehensive list of all of these methods, but alas, we are running out of time. And we have actually run out of time.
Damn right.
But before we finish off this video, you might have noticed that this video was a bit odd. Mainly because we have actually uploaded 3 videos just today. And that's because this isn't just a make it video. No, this is a part of the first charity checkpoint, the topic of which is the time evolution operator, which contains so much more. Link to the websites in the description where you will find multiple different papers going in depth about the topics we've discussed, as well as the topics we will discuss on stream. There will be more coming, there will be more papers, there will be more interactive things on the website, there will be an edit of the stream, there will be more videos, and everything will be coming along, so I would really recommend you keep checking the website regularly to see the changes. I would also like to extend special thanks to Ash for checking out the mathematics, for Remco for handling the physics, and Kaper for creating the website. It was a group project, it took a lot of effort, and I really hope you will enjoy. And for now, that'll be it. Thank you so much for watching, and have a great day. Bye!